You know that moment?
Yeah.
We've all had it. You're in front of the bathroom mirror, the light's a little too bright, and you lean in. There it is.
The intruder.
The intruder.
Yes.
That one, a single shimmering gray hair. And it feels, I don't know, so final.
It does. It feels like a biological signal, right? The beginning of the end, or so we think.
Oh, absolutely. The internal monologue is always, well, the factory's shutting down, the ink has run dry. It feels like this inevitable one-way street. But, and this is why I was so excited to get into this research today, what if that whole story is wrong?
A massive what if. What if the factory isn't actually shut? What if the workers are just stuck in the break room?
Exactly. That's the hook. That's the mission for this deep dive. We are looking at this incredible stack of research today, some huge studies in Nature from NYU and Harvard, data from the International Journal of Medical Sciences, and even some clinical trials in the Journal of Cosmetic Dermatology.
And the picture they paint is, well, it's surprisingly mechanical. It's less about this vague idea of aging and more about physical traffic jams and electrical overloads.
We're going to get into how the stem cells for hair color are actually these chameleons that can move back and forth, and how stress literally hardwires into our hair follicles to burn them out.
And the big takeaway, the potential for reversibility. If it's a mechanical failure, maybe we can fix the machine.
So let's start with that machine. For years, the old theory, the one you see in older reviews, was pretty simple and kind of depressing.
Right, it was just exhaustion. The idea that you're born with a finite tank of pigment. Or that over time, all this oxidative stress just kills off the pigment-making cells, the melanocytes.
Once they're dead, they're dead. No one's left to make the paint. End of story.
But this NYU study from Dr. Mayumi Ito and Dr. Chi's son, it throws a massive wrench in that. They found something really unique about these specific stem cells.
The melanocyte stem cells, or McSCs.
Exactly. Normally, a stem cell is on a one-way street. It becomes an adult cell, skin, muscle, whatever, and that's it. It doesn't, go back to being a teenager.
Right, it grows up.
But Maonies can. They are what we call plastic. They can move forward to make pigment, but they can also de-differentiate, move backward, go back to being a stem cell.
That seems incredibly complex for, a hair follicle. Why would we need that?
Because of the hair cycle. Hair is always falling out and regrowing. So the system needs to be elastic to ramp up, make color, and then ramp down and conserve its resources for the next round.
Okay, so if there are these magical de-aging chameleons, why do we go gray? Where does the system actually break down?
It breaks down in the geography. In the physical space of the follicle, the NYU team tracked these cells in mice and found the follicle has basically two rooms.
Two rooms.
You have the bulge, which is higher up. Think of that as the waiting room. It's a safe, quiet place for stem cells to hang out.
Okay, the bulge is the lounge, low lighting.
Exactly. Then lower down, you have the hair germ. That's the factory floor. When hair needs to grow, the stem cells have to physically move from the bulge down to the germ.
And that movement is the key.
It's everything, because the location determines the signal. In the hair germ on the factory floor, the cells are hit with a protein signal called WNT.
WNT. I feel like we're going to be hearing that acronym a lot.
It's the master switch. High WNT signaling means time to work, mature, and make pigment. But up in the bulge, the waiting room, WNT signaling is very low.
So the instruction there is just chill, stay dormant.
Precisely. The whole system depends on this commute. They travel down to the germ to get the work order, and then some of them even travel back up to the bulge to reset.
But in gray hair, the commute just stops.
That is exactly what they found. As the mice got older, these chameleon cells started getting physically stuck. They just pile up in the bulge.
They're jammed in the wrong room.
Yes, and because they're in the low WNT environment, they never get the order to make pigment. The crucial thing is they aren't dead. The number of cells is often the same. They're just immobilized.
Wow. So you have the workers, you have the factory, but the doors to the break room are locked from the inside.
And the hair grows out white. Dr. Sun concluded that this loss of motility, this inability to move between rooms, is a primary driver of graying.
Which, that immediately brings up reversibility. If they're not dead, if they're just stuck.
Then if you could find a way to nudge them out of that room, or maybe turn up the WNT signal inside the waiting room, you could theoretically turn the color back on.
The machinery is still there. It's just parked. Okay, but I'd play devil's advocate. That sounds like gradual aging. The getting stuck takes time. What about the stories we've all heard, going gray from stress?
You're giving me gray hairs.
Right. That doesn't feel like a traffic jam. That feels like a switch was flipped. Is that just a myth?
Not at all. It's a completely different mechanism. And that's where the Harvard study from Dr. Yachesu's lab comes in. They wanted to prove once and for all how stress causes graying. And frankly, the answer is kind of terrifying.
Terrifying how?
Well, first they ruled out the usual suspects. I think most of us assume it's hormonal.
Cortisol, right?
It's always cortisol. Or your immune system attacking itself. That's what they tested. They took mice, removed their adrenal glands so they couldn't make cortisol, and stressed them. Still went gray.
Okay, so it's not the stress hormone.
Nope. Then they tried immune-deficient mice. Stressed them. Still went gray.
So if it's not the chemicals in the blood and it's not the immune system, what is left?
The wiring. The sympathetic nervous system, your fight or flight response. It turns out those nerves run all the way down into every single hair follicle.
Wait, really? Our nerves are physically plugged into our hair?
The nerve endings wrap right around that stem cell waiting room, the bulge. And when you are under acute stress, they used a pain model to induce it, those nerves fire off a massive burst of a neurotransmitter, norepinephrine.
Norepinephrine.
Like adrenaline.
Very similar. And locally, in that follicle, it acts like a giant megaphone. It floods that quiet little waiting room.
And all those sleeping stem cells, they all wake up at once. It causes what they called hyperactivation. Instead of a slow trickle of stem cells to color your hair for a lifetime, the norepinephrine alarm bell makes every single one of them activate, mature, and leave the niche.
It's a stampede.
It's a complete bank run. The body spends its entire lifetime savings of pigment stem cells in just a few days. And unlike the stuck cells from the NYU study, once these are gone, they are gone.
That follicle is now permanently out of business.
Permanently white. It's a burnout. The system is flushed completely empty. And it really separates the two types of graying.
Right. One is a jammed gear that might be fixable that's aging, and the other is a catastrophic resource dump from stress.
And that's why managing stress isn't just about feeling better, it's about preventing permanent damage at a stem cell level.
Yeah, there was a third angle in all this that I found really counterintuitive. It was in that review by Lee, and it was about the speed of growth.
Ah, yes, the active growth theory.
This one confused me. The idea that white hairs might actually grow faster and thicker than colored hairs, that seems backwards.
It does, but there's a metabolic logic to it. Think of the energy cost.
Yeah.
It takes a lot of energy to build a hair shaft. It takes even more to also run the pigment factory at the same time.
So making color is an expensive add-on.
It is. And the theory is that if the hair is in a state of really aggressive, fast growth, all that cellular activity creates a lot of, well, metabolic exhaust. Oxidative stress.
And that exhaust can damage the pigment machinery.
It can damage the stem cells that support that machinery. And this links back to our friend WNT signaling. The International Journal of Medical Sciences paper honed in on one specific protein, 1T10B.
1T10B, another WNT signal.
A very specific type that acts as the gas pedal during the growth phase. It activates the pathway that tells cells to make pigment. In fact, when they overexpressed it in mice, pigment production went up.
So more 1T10B means more color.
To a point, yes. But here's the catch. If you're flooring the gas pedal for growth, but you're also creating a ton of oxidative stress, you might just be accelerating the burnout of your stem cell supply.
So you need the signal. But if you run the engine too hot for too long, you just break it faster.
Exactly. It suggests graying isn't always about stopping. Sometimes it's a side effect of a system running too hard without the right support.
Okay, so we've debunked the old cells just die myth. We now have cells that get stuck, cells that get screened out until they burn out, and cells that might get exhausted by overwork. Which brings us to the million-dollar question. Can we do anything about it?
Right. Can we fix it? And this is where we move from the lab bench to clinical observation. And I want to be clear, this is still early, but that study in the Journal of Cosmetic Dermatology on exosome therapy was, well, it was fascinating.
Exosomes. You hear that word everywhere in anti-aging now. What exactly are they?
If you strip away all the hype, think of them as nano-sized mailmen. They're tiny bubbles that cells release to carry messages, RNA, proteins, signals to other cells. They're little instruction packets.
Okay, and this study used exosomes from rose stem cells. I have to stop you. That sounds like something you'd read on the back of a very expensive face cream.
It's a fair point. The rose part sounds a bit like marketing. But the principle isn't about the flower. It's about using the generic repair and regenerate signals that plant stem cells produce in high quantities. They're full of anti-inflammatory and growth factors.
So they're just borrowing the plant's mailmen.
That's a good way to put it. In the study, they delivered these exosomes to the scalp using microneedling, or lasers, basically, creating tiny channels to get the messages down to the follicle.
And did the mail get delivered?
The results were surprisingly good. They saw actual repigmentation color returning to white hairs after an average of just over 2 sessions.
Wow, that's fast.
Very fast. And the effect lasted for almost 5 months. 60% of the patients had what they called a higher grade response, which is more than 50% improvement.
That's really significant. But there have to be caveats. Who did this actually work for? Because I'm guessing if your hair has been white for 20 years, this isn't the magic bullet.
You're right. It worked much, much better for people who had a shorter duration of graying, less than 10 years.
Which makes sense. If we're talking about unsticking cells, maybe there's a point of no return where they finally do degrade.
Exactly. Or the whole environment around them just becomes inhospitable. Another interesting thing, it worked better in patients who also had pattern hair loss.
Why on earth would that be?
The thinking is that in pattern hair loss, the follicle environment is highly inflamed and stressed. The exosomes might work so well there because their primary job is to cool down that inflammation and reduce oxidative stress.
And by doing that, they might be accidentally reactivating that WNT pathway we've been talking about.
It's highly likely. If you clean up the neighborhood, the stuck cells might finally get the signal to come out and get back to work.
So it's not a cure-all, but it's a powerful proof of concept. For early graying, at least. We're moving from just, painting over the problem to trying to fix the wiring inside.
We're fixing the machine instead of just painting the house.
So let's bring this all together. What does this really mean for you listening right now when you see that gray hair in the mirror?
It means we have to reframe it. It's not just getting old. It's a communication failure, a specific mechanical one.
It's a traffic jam. The WNT signal isn't getting through.
Or it's a system overload. The norepinephrine from stress is screaming so loud that the whole system burns out.
It makes you realize your hair is like a living record, a printout of your biological stress and your cellular logistics over time.
It is. And the fact that we can now distinguish between these different failure modes, stuck versus depleted, that's what's going to drive the next generation of treatments.
It really does give you hope that maybe one day, instead of reaching for a box of dye, you could use a topical that just coaxes those cells back into the right room.
We are getting so much closer to that. The biological roadmap is there.
But here's the thought that really sticks with me. We've been focused on hair. But if this stuck stem cell idea is real,
Right. That's the much bigger picture.
where else in the body is this happening?
And that's the question, isn't it? If stem cells and hair follicle can get jammed and stop working while staying alive, what about other tissues? Has regeneration in other parts of our bodies stopped just because the cells are stuck in the wrong place?
Could we eventually see gray hair, not as the sign of aging, but as the most visible symptom of a systemic traffic jam? And if we learn how to unstick those cells in our scalp, could we do the same for our skin or organs?
If we can learn how to clear these biological traffic jams, the implications are, well, they go far beyond just how we look. It could change how we define aging itself.
Something to think about the next time you spot that shimmering intruder in the mirror. Thanks for listening to this deep dive.
Always a pleasure.
Thank you for watching. Please subscribe, like, and share.